Namaskar, welcome back. So, this was the last slide where we stopped and we were discussing about that there are many regions which poses hazard to the Indian plate or Indian peninsula, and one of the most vulnerable region is Himalaya, as well as you have the Andaman and Nicobar region. Okay. Now, based on the historical data, what we have, the Indian portion has been like divided into multiple seismic zones, and now we have only 4 zones from 2 to 5. Okay. And 5 is the red one which has been shown up in the figure, which is the most vulnerable region. Okay. Now, formation of Himalaya, this process we have already discussed in the plate tectonics. So, we will move little bit quickly, but we will have will sort of browse on the things which we have discussed earlier. So, initially there was a subduction which was between the oceanic plate and the continental plate, that is your Tibetan side as well as the Indian side respectively, and then later there was no further uh, like ingredient of your uh, oceanic lithosphere going down. So, the volcanic activity ceased up on the Tibetan side, and then there was a collision which resulted into the formation of Himalayas. Okay. And at the same time, we also had a formation of basin in the foreland side, and that is what we have the Indo-Gangetic plains. Okay. So, this collision has resulted into buckling up of the areas uh, in the collision zone, and that resulted into the formation of Himalayas. And at the same time, what we see is that there are multiple weak zones which came up, and that is what we call the thrust zone, and which are attached to the low lying contact here, and that is what we call décollement. Okay, or the detachment. So, if you look at the section and the topography of the Himalaya, then we have the main detachment fault, and that is also termed as décollement, and we have 3 major ranges if we start from the north and come down to the south, and then we have the Indo-Gangetic plains. Okay. So, we have the higher Himalayas that we also call as an Hamadris, lesser Himalayas, and then Shivaliks or sub Himalayas, and then we have this one is your Indo-Gangetic plain. So, we have multiple thrust faulting or thrust fault systems which have been developed along the detachment. Okay. So, that is along this low detachment. Of course, this is the subduction boundary also we can say, and then we have the imbrications of the major fault systems which are coming up. So, from north to south if we take, okay, then what we have the this is what we call also trans-Himadri fault, or Indo-Sangpo suture zone is over here. Okay. Then we have main central thrust, which marks the boundary between the lesser Himalayas and the higher Himalayas. Then we have main boundary thrust, which marks the boundary between the Shivaliks and the lesser Himalayas. And then Himalayan frontal fault or Himalayan frontal thrust, we also call this as a Himalayan frontal thrust, and in some literature you will find that this is main frontal thrust. Okay. And the detachment which is there is also been termed as main Himalayan thrust. Okay. That is what has been shown here. Okay. So, overall seismicity if we want to look at, then based on the GPS studies and the seismic recording, it shows that most of the seismicity has been seen active between the MBT and MCT, whereas this zone, they say it is locked. Okay. So, this is locked area which does not move, but this keep on creeping. Okay. This area between MBT and MCT keeps creeping, and that results into the accumulation of strain in the frontal part. So, we performed a very simple experiment, what we call sandbox model, and that gave us an idea that how overall deformation would have started and how the different mountain ranges we see, because Himalaya is not made up of a single mountain range, it has different mountain ranges. Okay. So, you have higher Himalayas, lesser Himalayas and sub Himalayas, and the elevation also reduces as you move from north to south, as you have seen in the previous slide. Okay. So, we have elevation which goes, of course, the Mount Everest is above 8,000 meters, but we have the elevation, average elevation of the higher Himalayas is around 6,500 to 7,000 meters, and then if it reduces to 600 to 2,500 meters and less than 2,000 meters to 600 meters average in the sub Himalayas. Okay. So, how these fault systems were developed and keeping one plate moving. Of course, this is a model where what we did was that we have kept the flat surface not as an inclined what we see in typical subduction zones like this. Okay. But we have tried to keep this as a flat and try to understand that if you squeeze loose material, because the Indian plate or continental portion, in the front of the continental portion, the Indian plate had the oceanic sediments. Okay. Of course, along with the oceanic deposits or the sediments, the bedrocks or the harder crustal part, okay, was also deformed, and that what we see has come up in terms of the crystalline rocks and all that in Himalayas, or we also say metasedimentary rocks. The processes were there in terms of the formation of metamorphic rocks and all that. Okay. So, we see sedimentary rocks, we see metamorphic rocks, we also see igneous rocks if you go further up in Himalayas. At the same time, we also see the loose sediments in the frontal part of the Shivaliks. Okay. So, we did this experiment keeping, for example, you say that this is the northern side where we did little bit things opposite to have the understanding. So, but more or less this model what we got, or the deformation pattern what we got, was helped in explaining that how things have. So, the southern side is fixed, okay, this side is fixed, but the northern side is moving, okay, which is coming on the top of the Himalayan the Indian plate. Okay. So, if you look at this one here, then what you see is that there is an, when we start. So, you can look, keep eye on this, there is a screw here and this is a rigid plate that is moving. Okay. Now, this movement, if you look at, then we have the you can see the deformation has started over here, okay, slowly, and folds are developing. Okay. So, you can see the development of the first range over here. So, let us say that this was your higher Himalayas which started developing. Okay. So, at the time of the formation of the higher Himalayas, okay, we never had the other two ranges, that is lesser Himalayas and the sub Himalayas, we never had that. Okay. So, first the deformation started uh, with the condition that existed at that point of time, was the higher Himalayas started forming, and then we had an plain areas. Okay. And slowly what you see is that this portion is getting almost vertical, okay, and that is what we call the suture zone, Indo-Sangpu suture zone. Okay. And then frontal part, if you have, this is the Indo-Gangetic plain side, if we consider that, then we started seeing that there is some sort of a deformation. So, this sandbox model with the glass on either side, okay, helped us to see the deformation pattern, how the things evolved, okay, and the complete process in 3 dimension. Okay. So, where what we see is the topography is developing over here, okay, and then at the same time you have the formation of the faults here. Okay. So, if you see this one here, then you have the clear cut displacement, and slowly what we observed is that the deformation which was been taken up by this area has been transferred to further foreland side. Okay. And that is how we see a formation of different hill ranges. Okay. Now, there are theories which try to explain that what exactly happened, because one of the block will act as a rigid block or the wedge, because this we call the sliding wedge, and within this wedge there is ongoing deformation. So, now if the northern side block act as a rigid block, then the deformation has been transferred to the frontal part. Okay. But this never remains the same. It sometime take the deformation in the hinterland side, sometime it transferred to the frontal side. Okay. But most of the deformation is been transferred to the frontal side. Now, if the strain which has been developed because of this ongoing deformation is been released in the hinterland side, then those earthquakes we term that as an out of sequence earthquake. So, sequence what usually has been considered is that always there will be a deformation which will be transferred to the frontal part. Okay. But this never remains as it is. Okay. But so sometime you have the strain has been released in the hinterland side. So, that is out of sequence. Okay. So, that what we usually see. Now, if you carefully look at the final version here where we stopped, okay, then what you have is that this is your vertical, almost vertical. So, this is your suture zone, and then if you move further down towards south. Okay. So, this is your south, this is your north. Okay. So, we see a typical topography which has been developed over here. I may be having another video which I will show, and then it stopped here. Okay. And in section also you can see that there is a displacement where we took a sand of different colors, and that helped us in identifying the displacement. So, these are all thrust faults, and they are all merged over here. Okay. So, if you carefully look at, then they are all merged over here. So, this is typical of the deformation which has been transferred, or the displacement which has been transferred along the décollement. Okay. So, this becomes your main Himalayan thrust, and then you have, for example, you say that this is your this goes somewhere over here. Okay. So, this is your frontal fault, and then you have, we can say, MBT, and multiple splays of even MBT can also has developed, and that what we can see. Now, another important point here is that as it passes over here in this area, then after some time what we started looking at, the deformation has moved further up in this place. Okay, at this place. Now, this portion started taking up the deformation once this part, that is the hinterland part, became rigid. It acted as a rigid block. Okay. So, it pushed the frontal part, and the deformation was been taken up by the frontal region. So, we wanted to understand, and we never had this idea that how things will evolve, but this is what has happened. Okay. The sediment size also plays an important role. Okay. So, that we did in other experiment, and we were able to see a sort of a slightly different deformation. Anyway, let us move ahead and see what we have in the next video. Okay. So, finally what we were able to pick up was this portion. Okay. So, from here, if you say till this point, it took the deformation, it accumulated the deformation, but later on that acted as an rigid block. Okay. And the deformation was been transferred along in the frontal part with new faults, development of the new fault system, and of course of the hill range. Okay. So, you have a clear cut displacement which can be seen here. So, if we see quickly, this is what has happened, and maybe in the next, I may be having next one. Yes, okay. So, you have the next. No, that's over. Okay, fine. I'm sorry for that. So, anyway, this is what this part you should keep in mind, that how the deformation has been transferred to the foreland side. Okay. So, a steady state model, what it explains is that you have sort of an the formation of the faults in the hinterland side. So, initially this was been formed, and then slowly the deformation will be taken up by the frontal fault. So, the deformation will be towards the foreland side, and it also state that is the steady state model. It also state that the hinterland sides faults. Okay. So, this faults that is on the hinterland side. So, hinterland faults will become inactive, but this is not true. Okay. Because we were able to see and identify the active fault topography. In the hinterland side also. So, this active fault topography clearly indicated that the steady state model does not stand if we look at the ongoing deformation in Himalayas. Okay. It also have or take up the hinterland side also take up the displacement in some short of an period, but most of the deformation has been transferred to the frontal part. Now, based on the strain accumulation and the strain release and the amount of slip which is available, or we can say potential slip which is available, and the potential of Himalayas or the Himalayan zone to host an earthquake has been shown in this figure. Okay. And this is after Bilham, which talks about the figure talks about the possible slip available in gap areas. Okay. Now, what are these gaps? So, if I am not wrong, we had discussed about the seismic gaps in the past. So, what basically the scientific groups have done, that for example, if I am just putting this as an schematic diagram. So, if you have for example, the area like this, and we say that this is an Himalayan arc. Okay. Now, there was one earthquake over here. We can talk about, we can say that there was a Kashmir earthquake in 1555. Then we have another one was here 1905 was Kangra, and then another was 1934, and then here somewhere over top UK Assam is here 1950. Now, based on this, what they suggested was that the area which exists between this major earthquakes are your seismic gaps, where we have the potential of having earthquakes over here. Okay. Whereas here, so we have potential here in this area, but this areas have released the strain. Okay. And that is exactly, so seismic gaps, this is Kashmir seismic gap. This one is the central seismic gap, we say. So this is central seismic gap, and this has been termed as Assam seismic gap. And you can see that this is based on the earthquake which has been triggered or observed, that this is 1934 and 1950, then you have 1905 and so on. Okay. So this area is been termed as your central seismic gap. Now what has been shown here, that in 1934 the strain was released. Okay. So this is what your strain is. It has been released by major earthquake. 1905 the strain was released, but the regions which are adjoining this or in between this major earthquakes are having potential to slip. Okay. So there are the possible slip is there. So potential slip has been given here, that it can have the potential slip of almost like 10 meters, okay, on fault. And then what is the possible magnitude you can expect from this? Okay. So the areas which are shown with the red and pink boxes or the bars, that those areas are having potential of slip from 8 to 10 meters and can trigger earthquake up to 8.2. Now, how far this is true, that is a major question, okay, or we can say that is one of the main question we can ask. Okay. So the question we can frame in such a way that whether this 1905 earthquake, for example, we take Kangra, whether this 1905 earthquake was triggered by the Himalayan frontal fault, because in previous slide what we have seen that there are multiple fault system. Okay. You have MCT, MBT and HFT, or you can say main Himalayan thrust is that one, but main frontal thrust. So you have this three fault systems. Okay. Now whether this 1905 earthquake was been hosted by Himalayan frontal thrust or it was been hosted by the hinterland fault system. Now if it was been hosted by the hinterland fault system, then still this area has potential to trigger, because in the frontal part you have this accumulated strain over the time which has been still left out. So in this case, this area according to us has potential to trigger major earthquake in near future. So what we are trying is, we are trying to look at that if you see the plan view, then you have the Himalayan frontal fault, then you have MBT and then you have MCT. Okay. So Himalayan frontal thrust, then you have main boundary thrust and then MCT, and of course there are splays of faults which are also sitting over here. Okay. Now which one of this fault or which one of this the earthquake was been hosted by which one of this fault actually? That is a big question, whether it was MBT or it was HFT fault system or it was MCT fault system. Okay. So what we did was, we started identifying the active faults, and then we learned that the 1905 earthquake. So we have a paper, of course, there has been debate, but yes, of course, the debate should be there in scientific world. Okay. So our suggestion is, or our inference is, that 1905 earthquake was been hosted by the hinterland fault. Okay. So we identified a new fault which was been named as Kangra Valley fault. We will discuss that the topography, active fault topography in Kangra Valley, how it looks like, and on what basis we say that the 1905 earthquake was on Kangra Valley fault. So according to us, we say that still the potential is available in this region and can trigger. And similar proposition is for the your other areas also. So, how far we say that this seismic gap theory is true, okay, or the whole area of Himalayan region is capable of hosting earthquake of large magnitude and great Himalayan earthquakes. Okay. Great Himalayan earthquakes, when we say that, it goes above 8 magnitude and less than 8.5 or up to 8.5, but large magnitude is above 7.5 and less than 8 magnitude. Because when you look at the historical data, whatever in whatever form it is available, then that clearly indicates that there was no period in terms of the centuries in the past which did not host the earth or did not record the earthquakes. The earthquakes were been experienced in the past. Okay. So, that part is also another uh, uh, kind of a work which we did, okay, and we were able to publish a sort of an compiled database on a review paper on that, that how we say that this could be there are possibilities of having earthquakes even in the seismic gap regions. Okay. So, seismic zonation map which exists today is just based on the historical accounts. Okay. So, we had like 1555 earthquake, 1905 as I was discussing, and then we had 1505 another earthquake in the central Himalaya, and then we have 1905. Okay. So, based on that those earthquakes, this seismic gap theory has evolved. Of course, the gap should be identified but with the complete data or the best data if you can have. Okay. So, one can implement the paleoseismic investigation where we can like unearth or try to identify the signatures of the past earthquake preserved in the geological records, okay, and also the geomorphological records what we see on the surface. So, that has to be done, and since we have multiple faults which are been evolved or which are the part of the major fault systems, how they have behaved in terms of hosting earthquakes in the past, that has to be understood well. Okay. So, there are now if we see this was in the past, like we had couple of paleoseismic studies, but now if we try to see, then we have almost like 50 plus trenches which have been done along this frontal part. Okay. So, we have good amount of data. So, now we can have, even one can do modeling, we can try to understand that what is the recurrence interval, how long was the rupture of the past earthquake, that those things can be uh, you can extract from this information. Okay. So, now further looking at the active fault topography, this is from the Kutch region, which we did mapping, where we did mapping after 2001 Bhuj earthquake, and as per our understanding and what we the aerial survey we did, okay, we identified the active fault, okay, but unfortunately this active fault did not move, or there was no displacement observed during 2001 Bhuj earthquake. So, again the question remains that when this type of uh, uh, faults move, okay, during what would be the magnitude of the earthquakes which moves or displacement is seen along this type of faults. Okay. Either we can say that it needs more sort of a larger magnitude to have the deformation coming right up to the surface. So, these are few questions with which we moved and we did paleoseismic studies. Okay. So, the trenching was been conducted over here in this area, where we see a very low scarp. Okay. So, you have a very low scarp over here. Okay. this is south and this is north. Anyway, we'll stop here. We'll continue with more details on the deformation pattern in compressional tectonic environment in next lecture. Till then, thank you so much. Namaskar.